Alright, so let's recap what we were trying to do. Right, remember we want to describe the cohomology ring of the torus, and we want to start by giving a vector space basis for this cohomology. Now, we claim that a basis for this is going to be given by 1 alpha beta and the wedge product of alpha and beta, where alpha and beta are defined as follows. Alpha and beta are just going to be the one forms on the torus whose pullback are exactly dx and dy, where x and y here are the coordinates on R2. Now, what is not clear here is that there will exist such alpha and beta. In other words, how do we know that dx and dy lie inside this image? Thus, we proceeded to find out what the image of this is. And we claim that the image of this pullback map, the pullbacks of the forms on the torus, are exactly the forms on R2 that are invariant under translation by the lattice element. Previously, we have proven this containment, i.e., if we have a form on R2 that is the pullback of some form on the torus, then it must be invariant under translation by lattice element. Now, we want to prove the opposite direction. Alright, so let omega be a smooth form on R2, such that omega is invariant under translation by element of the lattice. Where here, remember that L lambda is the map from R2 to R2, sending it with point P to P plus lambda. Thus, point-wise, we have the following description for the pullback of omega under translation. So if VI's are tangent vectors, right, in the tangent space at P, then the value of this pullback at VI, by definition, is just going to be the value of omega at the push forward of this VI. Thus, in particular, if omega is invariant under translation by lattice element, then we see that this left-hand side is equal to the value of omega p at VI. Thus, we have the following equality for all point P in R2, all lambda in the lattice, and all tangent vectors VI in the tangent space to R2 at P. Now, let's have a look at the picture and see what this is saying. What we just said is that if we translate this point P by a lattice element lambda, and let these vectors be the push forwards of this vector VI under this translation by lambda map, then the value of omega on these vectors is the same as the value of omega on this vector. Now, this means that omega descend to a well-defined map omega tilde on the torus. More precisely, omega is going to be the pullback of this map omega tilde on the torus, where we define this omega tilde as follows. So let's say we're given a point P tilde here on the torus, and tangent vectors VI tilde at the tangent space to the torus at P tilde. Then we define the value of the form omega tilde P tilde on these vectors to be the value of omega P on V1 VR, where P is any preimage of P tilde, and V1 VR are any preimages of this VI tilde under the map on tangent space, because observe that the map on tangent space is an isomorphism. Now, from our previous discussion, this omega tilde here is well defined, because any other preimage of P tilde is gonna differ from P by some lattice element. And we have mentioned that if we translate this by a lattice element, we get the same value. Thus, we see that when omega is invariant under translation by the lattice lambda, then it is the pullback of some form omega tilde on the torus. This concludes the proof that the image of this pullback map are exactly the forms on R2 that are invariant under translation by the lattice. In particular, dx and dy are obviously invariant under translation, actually by translation by any constant, not just translation by lattice element. So then, by this statement here, these must lie in the image of this pi star. In other words, they must be pullback of some form on the torus. So let us define alpha to be the form whose pullback is dx and beta to be the form whose pullback is dy. In the next video, we're gonna show that a real vector space basis for the cohomology of the torus is given by 1, alpha, beta, and the wedge product of alpha with beta.